Good evening and welcome to tonight's nanoTalks. My name is Schröter and we're streaming the nanoTalks once again from my home. It is my pleasure to welcome all of you to the nanoTalks in this digital format. I will give you a quick introduction to what is happening this evening before we'll hear the interesting talks by Karin Schröter. Oh shit. My name is Schröter and we're streaming. Before we'll hear the very interesting talks by Karin Schröter and Chiara Gattioni. And after the talks, you will have a chance to ask them questions in a Q&A that I'll explain later on. The nanotalks are organized by REACH. REACH is an independent think tank that is working to establish a science-friendly culture. In our view, a science-friendly culture is a place where science and society work side by side and not one against each other. If you're interested in REACH, you'll get more information on our website about REACH. It's www.reach.ch. You can join our over 200 members in Zurich, Bern, Basel, Lausanne, or at the moment anywhere online in Switzerland. You can sign up for our newsletter or you can become a member. And I'd like to take this opportunity here now to point out two current programs of REACH that could be of interest to you. The first of them is the SIMPACT program, which is REACH's training program to train future decision makers, future scientists in how to communicate science. And one of the formats we use for this training typically is the nanotalks. If you're interested in learning more about SIMPACT, our program where 25 young people will be trained in how to do science communication and public outreach, you'll find more information about this at www.simpact.reach.ch, as you can see here. And you have until the end of September, so one more week, to apply to be a part of this program for the second round that is starting soon. Another program that REACH currently has running is a competition for clever ideas on how science can deal with crises before they even come up. If you have an idea like this, you can submit it to the competition until October 2nd or 3rd. If you submit an idea, it will be evaluated by a high-level jury, and the best ideas get a monetary prize of multiple hundred francs. You'll find more information about this competition for ideas on the REACH website. You can't miss it there. Or if you have questions, one of our board members is live on our Instagram tonight, answering questions in the story there. Now, I don't want to keep you further from the talks, but before we go into the actual content, I promised you there was a way that you could participate, ask questions during the talks, and the way you can do this at any time is to go to www.sly.do and enter the code nano-sept. You'll also find this description and this information in the description of this video. If you go to this website, you can just ask a question, and after both talks are through, I will then moderate the Q&A with our two speakers. So at any point during the first talk or the second talk, you have a chance to post your question there or upvote questions you see that you find particularly interesting. With all of this out of the way, we now come to the content that you've come for tonight. Tonight's two nanotalks about technologies for the future. The first talk about hydrogen technologies will be given by Karin Schröter, who is an engineer at Empa, and she came here today by car. Unfortunately though, it wasn't a hydrogen car yet, but she will tell us more about what needs to happen so that she and all of us can hopefully drive hydrogen cars in the near future. With this, I welcome Karin.
Thank you very much. for the introduction and welcoming me here. And welcome to all of you to the nanoTalk about hydrogen and future mobility. And when I talk about future mobility, it's a broad topic. I mean, how do we get people from A to B in the future? And there's also still that's also still a broad topic. And we have on the one side the social stuff, and also will we use artificial intelligence for driving, car sharing, will we use self-driving cars, public transportation, and all this stuff on the left side. When I talk about future mobility as an engineer, I think about the powertrain, and with this, the most common topic now is how do we get them CO2 neutral. So, for example, if you drive an average gasoline car, you produce 13 kilograms CO2 per 100 kilometers. So that's a lot of CO2. And there are approaches to reduce them with hybridization, or also approaches to really get CO2 neutral. And the first one that's always mentioned is the battery electric vehicle. And with this, you are CO2 neutral because you don't have direct CO2 emissions. And when you have solar panels on your house and you only drive short ranges, you are CO2 neutral. But on the other hand, this technology has also disadvantages like the short ranges in general, then the long refueling, or in this case recharging time, and for everyone to really drive a battery electric vehicle, you would need infrastructure with a whole lot of more renewable energy and charging stations. And this is very complicated. So the other possible opportunity to go CO2 neutral in the powertrain system is to go to fuel cell vehicles. And these vehicles have electric engines powered by fuel cells that are powered by hydrogen. And with hydrogen, you only get water emissions. So for the instant emissions, you are equally CO2 neutral than battery electric vehicles. Hydrogen itself is the most common atom in the universe. This means it's all around us, but not like pure hydrogen at the moment. So the technology of fuel cells is also very old. We have it like the first experiments happened in 1838. And for example, NASA uses fuel cells from the 1960s up till today as the main power source for their space programs. And also in transportation, like public transportation, there were first prototypes of fuel cell vehicles in the 1990s. So this technology was there about 30 years ago, and since then there was a lot of research on fuel cells and hydrogen production, but it had not had this hype. And this is simply because there are cheap and easy accessible alternatives like oil or methane gas, and they always kind of let the hydrogen hide itself. Also, hydrogen is very, it needs proper handling. To put it simple, it's a very small molecule, and because of that, it's very diffusive. So, and also it's very explosive. And when people think about hydrogen, their minds always blew up. Like they think about explosions, like for example the Hindenburg, or also a topic that's always mentioned is the hydrogen bomb, but which has nothing to do with hydrogen in the mobility sector at all. As I said, proper handling is needed, and today we can really do that in an amount that hydrogen is as safe as gasoline. So it's still relevant because hydrogen has, as I said, no direct CO2 emissions and a very high mass-specific energy density. You can see this here. Hydrogen has about, or even double the density than gasoline or diesel. On the other hand, the volumetric density of hydrogen is very low compared to liquid fuels. So this is a problem for a sector like transport, where you don't not only have weight problems, but also volume problems. But when you change from a conventional vehicle to a hydrogen vehicle, you don't have to adapt that much, as you have, I think, nearly the same range, nearly the same fuel price for one refueling, and also a similar refueling time compared to gasoline vehicles. So that's a very a good advantage compared to battery electric vehicles. And also hydrogen is a chemical energy carrier. This means it can be better stored and transported than electrical energy, or more efficiently transported. On the other hand, the whole hydrogen process in the mobility is not as efficient as the battery or electric vehicle. But with renewable energy, we still are CO2 neutral. For this whole thing to really happen, so for hydrogen future mobility, we need the infrastructure though. So it's similar to battery electric vehicles. We not have the infrastructure yet, but we need it to go forward. And speaking of infrastructure, here you can see the move. That is the first hydrogen refueling station in Switzerland, built in 2016. And I will show you how we brought this whole thing of producing and refueling hydrogen to Switzerland. Here you can see this whole process from the start, from the production to a storage to the refueling. And we go through it from the start. We start at the hydrogen production, as I said. And in our case, we produce hydrogen with electrolysis. And this has an efficiency of above 50%. So it's still very efficient, but it's not that efficient as if you would use directly the electrical energy. And all our electrical energy is produced renewable. For everyone that is a little bit unsure what electrolysis really is, it's the process of dividing water into hydrogen and oxygen with an electric current, and also a membrane that separates the cathode from the anode. So in our case, it's a proton exchange membrane, short PEM. And this is the reverse process of the fuel cell. So in this case, you put electric energy inside of it, you get hydrogen out, and the fuel cells put hydrogen and oxygen in and get electrical energy out that fuel the electric engine. In the move, we have 180 watt installed electrical power electrolysis. This means we get about 2.7 kilograms hydrogen per hour out of this system. And when we have them, we need to store them. And as you see, it's not that easy, and this means this is because hydrogen has a very, very low density. When you have normal conditions and you want to store 1 kilogram of hydrogen, you would need 11 cubic meters for this. Or the other way around, if you would have a tank with 1 cubic meter, you could only store 90 grams of hydrogen. Our electrolyzer produces hydrogen at 30 bar, so we can reduce the needed volume a lot. But for vehicles, this is still too much volume. And so currently the trucks are using hydrogen at 350 bar, and the passenger vehicles use hydrogen at about 700 bar. And in our system, the highest pressure is 900 bar, because we fuel only because of the pressure difference from our tanks to the vehicles. And with this 900 bars, we can reduce the needed volume from originally 11 cubic meters to 0.02 cubic meters, means it's about 0.2% of the original volume. But not every material holds this pressure, especially with hydrogen. So we have composite material cylinders This means we have a polymer inlay and carbon fibers around them. And here you can see there are 12 tanks. 6 of them are filled with 30 bar and 6 with 440 bar. And we have our high pressure stage here. These are 20 cylinders with 900 bar. And this whole thing has about 7 cubic meters and 150 kilogram of hydrogen stored on this small volume just because of this pressure. As I said, we go from the storage to the refueling, but first we have another problem to solve, and this is the pre-cooling step. Because of this pressure change from this 900 bar in our tanks to our vehicle tanks that have a lower pressure, we have a heat development. And this can be up to 100 kelvins in one refueling. So our vehicle tanks can only handle about 80 degrees Celsius. So we need to pre-cool the whole hydrogen to minus 40 degrees before we can really put it into the car to avoid damage. And there are a lot of simulations and projects about this whole hydrogen refueling and heat development in these tanks. Now, from the pre-cooling to the fueling, we have, as I said, 2 refueling stations, or it's one. On the one side we have the 350 bar, and on the other side 700 bar. And with this setup we have about 5 minutes refueling time and sell the hydrogen for 10 francs per kilogram. In a normal passenger car, they fit about 5 kilograms. And I really wanted to show you this nozzle here, because I think that's the most interesting part, because everyone always thinks it's like something strange or from the future, but it quite looks not that technically challenging. It is. It has an infrared sensor in this around the gas channel, and when you couple it to your vehicle and you press here start, the whole thing first checks if the pressure is right, if the temperature is right, and if there is any leakage. And only if everything is okay, this whole process starts. And so you don't have to fear when you stand near a hydrogen refueling stations that something is going out and blowing up. As I said, this is the process we have in the move, and it consists of a hydrogen production, hydrogen storage, and the hydrogen refueling with pre-cooling. And now is the problem, this technology is very new, so this process, or these technologies are needed, but every hydrogen refueling station has them to a different level or uses other process steps or other technology. So you cannot say every refueling station looks quite really exactly like ours. Some only have one pressure stage, and some get their hydrogen transported over a little bit of distance. And I say this is only the one we have, but the technology we have is really the one that is needed for hydrogen infrastructure. And currently there are 3 hydrogen refueling stations in Switzerland, and that is really not enough to have everyone to cover it with hydrogen. And there still needs to be this infrastructure built. And one of these projects that really looks out to develop or to introduce hydrogen refueling stations is H2 Energy. Together with Hyundai, they want to introduce 1,600 hydrogen trucks to Switzerland and build this refueling infrastructure. And if you want to look where is my nearest hydrogen refueling station, you can look at either of these maps. And when you really want to buy a new hydrogen or fuel, if you want to really buy a new fuel cell car, you now have to settle for one of these models at the moment, but I hope there will be more in the future. And when I say now future mobility, what I think about is I hope some of us can in the future drive with hydrogen, producing only water in this process, because it is a CO2 because it is a CO2 neutral alternative if we really implement this infrastructure. And I want to thank you very much for your attention. And if you want to know anything more about the move and all these projects we are doing around it, you can go to this website. So thank you very much and have a nice evening.
Thanks a lot, Karin. That was a really interesting talk. Now, I mentioned before, you can all ask questions to Karin and afterwards to Chiara. You do this just as a quick reminder by going to www.sly.do and enter code nano-sept. You'll find the same also in the description of the video. And now let's continue and go to our second speaker for the night, Chiara, who is a postdoc at the Department of Materials. And I've been told that her cat may or may not make an introduction because she's not actually here with us, but live with us via Zoom. She will give the second talk about tribology, or a bit more understandable, at least to me, the role of lubricants and how they make technology greener. Chiara, you should now be live. Yeah, you're now live here. Please unmute yourself.
Hello, can you hear me?
Yes, the floor is all yours.
Thank you very much. Thanks everyone for joining in, and thanks Reach for having me. So I will spend the next 15 minutes or so telling you why lubricants are really important in our fight against climate change, and they look so ordinary, or we think of them as some really ordinary things, and we actually don't really think about them at all. But actually there are complex engineering systems which have really great potential for reducing emissions and making automotive systems greener. So, okay, hold on here. So we already heard the talk from Karin, which was really nice, about one way of greening, of making automotive systems greener, and that is changing the way we fuel them, so that in order to reduce or make them carbon neutral. And I think that on top of this, we should also give a thought about what are the ways in which we can get our automotive systems to basically use less energy, so that we can do more with less fuel. And it's actually not only automotive systems, but all sorts of machinery which is powered, like industrial machinery, for example. So there is a really vast range of systems which can really be improved by thinking on how can we reduce the amount of energy they use. And not only the amount of energy, but the amount of material, material sources. So let's take the example of a car, because we are familiar with it. So there is, for example, materials wear from the friction between the tire and the tarmac, or there is corrosion, which also means that materials is consumed and has to be replaced, and that comes to an energy and material cost. And then every single moving part within our car, within our automotive system, will have some friction to overcome, and overcoming friction costs energy. So I would like to kind of get you to think during this talk that we can think of all these problems as an additional things that's really important to think about when we think about making our automotive systems greener. Now, this these three problems that I've talked about, which are just an example, they all come under the umbrella of tribology. So tribology is the science of the engineering discipline which studies friction and wear and way to overcome friction and wear. So for example, lubrication. And I would like to kind of digress for 1 minute and talk a little bit more about tribology, just because it's such an important engineering science. And generally, people who are not in engineering have actually never heard of it. So if in this moment you're sitting down and you're eating a snack, the contact between the food and your teeth, that is a tribological contact, because you're sort of moving your teeth against the food, and there will be like friction and wear acting there. Or, you know, when I move my hand like this, the bone and the socket, that is a tribological contact, and the synovial fluid that is lubricating it is the lubricant. So there is a whole area of tribology which deals with the body, and you know, that's also like creams and hair products. That's all biotribology. Then tribology can look at a really large scale, so tectonic plates moving against one another. That is a form of tribology. They call it geotribology. And it can look at a really, really tiny scale. So what I'm showing here is a microelectromechanical system. It's just a really tiny cogs that's actually really hard to make move, because there's such high surface energies and they need really special lubricants. So tribology is not only the car, is not only lubricant in your car, but it's really a huge field, a huge discipline. And I will just talking about a really tiny element of it. And however, even just this tiny element is really important. So the reason why I think that all of us who do like this research in lubricant engineering think it's really worthwhile is because a large part of the world total energy consumption comes from tribological contacts. So there's various reports. These numbers I've taken here are from this report, but you know, a quarter of the world energy consumption comes from overcoming friction and wear. So that is a really large amount. And the way we can overcome it is, you know, designing better contacts, designing better materials, designing better lubricants. And by looking at what savings can be done with these novel designs, transportation is actually one of the fields, of the areas where a lot of energy can be saved with this by taking action now and implementing novel technologies. So I strongly believe, I feel passionate about the fact that this is really an important way to tackle going carbon neutral. Right. So within this framework, I want to talk about lubrication science, because this is what I do. So as I said, so lubrication science is about lubricating a contact and reducing the friction. So this is an example of this is, let's say, two ball bearings or two surfaces in contact. So when they're in contact, and you can just try, you know, with your hands, and you press them and then you try to slide them. You have to apply quite a lot of force to move them. So this is having high friction. And now, if we take them and just rub an oil or a cream, and you do the same, then the hands would slide much more easily. And so why is it? How does a lubricant work, and what is a lubricant? So a lubricant is a liquid which has fairly high viscosity. So this is an alkane oil. molecule. So this is a way how you can have high viscosity in the liquid, is having just a really long molecule. And basically what happens is that all these long molecules get tangled together a bit. If you ever try to take spaghetti out of a of a bowl, that's how it looks like. They're just tangled together. And so when you move them by pouring the liquid, for example, they first have to disentangle themselves, and so that they're able to move. Having something with high viscosity makes quite a good lubricant. Now, when we just add it to our contact, to our two surfaces, a little bit will go in the middle, a lot of it will go outside. So it will provide some separation already of the two surfaces. So we already go from something which is completely, like, really hard to move, to something which is a little bit easier to move. Then when we take our contact with the lubricant and then we move it, what happens is that the movement sucks all of the molecules inside the contact. And also with time, it kind of moves them and rotates them so that they're aligned. And you form a nice film which separates the surfaces. And so the way that reducing friction works is that when you're moving these two parts, these two components, all you're doing is having these long molecules sliding on top of one another, which is much easier in terms of the energy that you have to provide to the system than having two solid blocks with a lot of asperities trying to slide on top of one another. So this is how a lubricant works. And okay, from what I say, it might sound that we have it all worked out, right? Like we know how a lubricant works, we know that we need a certain viscosity, but actually there are still a lot of challenges in lubrication science, and I will just talk about one, but I think it should kind of give you an idea of what we need to think about when we are trying to improve a lubricant and make it more efficient, and in that way reducing the friction. So one example that I want to talk about is that of boundary lubrication. So maybe I'll start from here to explain boundary lubrication. So boundary lubrication is this case. So it's the case when your surfaces are not moving and you have the lubricant, and so there's not the formation yet of this nice thick film which you get when the surfaces are in movement. You have that the surfaces are still quite close together and there is a bit of lubricant in the middle. The same thing could also happen when the surfaces are moving, but there is really a lot of pressure pushing them together. But for now, let's think of these surfaces being static. And maybe the way one can try and imagine it is the moment that when you switch on your car. So when your car is switched off, you have this situation. All the components are static and there is the lubricant which somewhat separates them. And you have to go from this case to that case. And to do that, you have to build this film and overcome basically the friction that you have when you don't have a nice thick film of a lubricant. And to visualize it a little bit better, let's just think of an engineering component. So these are ball bearings in their casing. And if you look at them, they look like beautifully shiny, like mirrors. So one would think this surface is completely smooth. Actually, when we go and look really at the nanoscale, this surface is not smooth at all. It's really, it's got asperities. It's a rough surface. So the yellow thing is the lubricant, and there's the gray is the two surfaces in contact. So when we have the surfaces are not moving, and we have just a very thin film of a lubricant, a lot of the asperities will be in contact. And so what happens to go from the static to the moving scenario with a nice thick film is two things. First of all, there will be a lot of energy spent to overcome this friction of this asperity moving. And secondly, this asperity will get damaged. So we will also have wear, which will then produce debris. The debris will remain in the system, and overall, it will end up damaging the system. So boundary lubrication is really a big problem and is really a big energy expenditure in all machinery with moving parts. It's really the startup when you turn on the engine. So the way to do it is to try and find a way then to never have this scenario, never have the asperities in contact. So and so this is something I have worked on. And so the way to do it is to have additives, to add additives into the oil. So in this case, there will be friction modifying additives, they're called. So if you remember from a few slides before, the oil, it looks like this. It's these long carbon molecules with hydrogens. And the additive looks very, very similar, except it has a little different head, which is polar. So the polar head is here. So what I have here is a description of a contact. So these on the top and the bottom are the surfaces of steel. And then here in white and red are the polar heads, which are these ones, which are attached to this steel surface. And these little vertical spaghetti here are the non-polar tails. So what happens is that basically this molecule will really compactly get stuck onto the surface and form two little bristles, which make sure that the surfaces are always separate. And as you see, the tails are the same as the base oil. So there are no problem really with the interaction between the tail and the base oil, because they're basically the same thing. And then when this thing starts to slide, the film will build up eventually. But even at the very beginning of sliding, this oil that will not have to will not have to kind of compete with the asperities. It will sort of, the tails will just do the job basically of the oil in keeping the asperities separate. So this is how we design modern oil, is by trying to understand what are the problems to overcome, and finding an engineering solution or a chemical solution to this problem. And other problems that could occur are, for example, in hybrid cars, which have also an electric engines, there will be a lot of copper parts which easily corrode. So in that case, what we want to do is to make sure that there's ways to protect all these surfaces from corrosion. And so there will be a different additive which will do that. Or there are certain materials which will wear very easily, and so there will have to be anti-wear agents. So in the end, what one ends up with is a really complex and customizable multi-component system, where we have some components that will attach to the surface, either to protect the surface, for example, the corrosion inhibitors, or the anti-wear agents, or these friction modifiers. They're not to protect the surface, but they're to keep the surface separate. Or there will be viscosity modifiers, which, for example, might kick in at a certain temperature when the viscosity of the base oil becomes too little. Or there will be more technical components, I suppose, like anti-foam agents, for example. And sort of the whole idea of lubrication science is to tune this zoo of inhibitors in a way that improves the performance. And this comes then with its own challenges. So, for example, the friction modifier that I showed you just now, so with the polar head and the long tail, is actually an acid which will eventually corrode the surface. So although it really helps at startup, then it has other effects down the line. So a lot of research that what we are doing is that, okay, can we find something that works as good as a friction modifier without, in, I don't know, 5 years' time, completely destroying the engine or wherever it is put. Or there's, for example, the most common and the most useful anti-wear agent was actually highly toxic, and so had to be removed at some point from the market. But nobody has found anything which works quite as well. So there is really always a work in progress in introducing new components and understand what they do to the system. So it is a really always a work in progress, and hopefully we are sort of slowly tuning the chemistry to find the best possible results. Okay, so with this, I would like to conclude. So I showed you one example of how we try to build better lubricants to produce better tribology for automotive system to eventually lead us to energy savings and a carbon neutral world. What I showed you is improved formulation of lubricant and lubricant additives. And but as I said, this is just one aspect of tribology, and there are a lot more, like different like greases or different surface coatings that are also becoming more and more relevant. So I hope that you found this interesting and you will look with renewed interest at your car lubricant. And I would like to thank you all for your attention.
Thanks a lot, Chiara. From our side here, it was a really interesting talk. Certainly learned a lot there on areas I wasn't really consciously thinking about where lubrication would be playing a role. We're in the Q&A phase now of the nanoTalks, which means participants, you can continue to send in questions on slide.do. You will find all of the relevant information in the description of the video, and we'll start the Q&A now. Thanks again both to Karin and Chiara for giving the interesting talks. Let's start with a question to Karin, so that Chiara had a short break in talking. Maybe to start with quite a simple one. You showed that trucks and cars have quite different pressures in the hydrogen they store. Why is that?
First of all, it's no legal binding pressure level or something like this. It's just the mainly used one today. So the trucks have a lot more space, so they don't need this high pressure, so they can use it at 350 bar. And we could also fuel trucks with 700 bars if they had the same tanks. So the main problem for hydrogen is really the density, and for vehicle cars you wouldn't want to drive around with a real big tank behind you, but in the trucks it's not that big problem.
Okay, well, that makes a lot of sense. Then maybe the intro question to you, Chiara, is of the tribology research that you describe, is this a lot of academic research, or is it a lot of research that is being done in industry?
It's both, actually. So in industry, there is a lot of new secret molecules that people want to try as new additives. So there is really a lot. In academic institutions, there is new known secret molecules, but also I mentioned that, for example, there are some systems that there's just some fundamentals that we don't really understand. So I talked about this anti-wear agent that it has to be removed from the market because it's toxic, but it worked amazingly and nobody knows why. So if you don't know why something works so amazingly, it's then really hard to build something else which works as amazingly. So a lot of the academic research works at this level, really try to uncover why things work in a certain way and how can we build on that knowledge.
Have we heard of this agent that has been removed from the market? Is it like a term that...
It's not a secret, it's zinc something. I always forget the long name. So yeah, no, it's...
And has it been off the market for long, or is this a recent removal?
I think it probably depends on the country, but it's not been many years. It's not been many years. It was just it was just strong, like it was just really corroding parts of the car, and it just had to be.
Okay. Yeah. Huh. Fascinating. Well, speaking of cars, let's go back to Karin. Another question that came in is that if we, to get to greener cars, need to build a new refueling system, why should we be going for a hydrogen system and not just an electric system? Aren't Teslas all the rage nowadays? What are the benefits of going to a hydrogen system there?
So first of all, I think, and all my group thinks, there's no one solution technology. So I really like electric cars, and it's a very good use for short ranges, as I said. The other part is you have a long refueling time, and some people that are driving cars, for example taxis or buses, or cannot wait that long for their short ranges. So this is one point. The other point is, when we speak of infrastructure, to have everyone get an electric car, we would need this high voltage grid to every household. And for hydrogen infrastructure, we only would need a few, I think in the tens or 100 refueling stations in whole Switzerland to have this infrastructure for everyone. And the hydrogen production sites are one big part, but they could be at, for example, hydropower generations. And so there would not be that need of this high voltage grid in that extent. But I think if we combine all these solutions and also synthetic gas and synthetic fuels, I think we can be CO2 neutral. Another part I thought about is when you think of batteries and their energy density, their weight-specific energy density is comparable very low. And I said we have 150 kilos at the move in 7 cubic meters. This is a power of 5 gigawatt hours that we have in 7 cubic meters volume. So this is really the big point why we go from electric to methane, to hydrogen, to methane, to all these synthetic fuels to get a higher energy density and also the storage capacity, because renewable energy is not very easy stored.
You said there are 5 gigawatts of power in this relatively small thing. How big of an area would you need to store the same in battery?
I'm sorry, I cannot tell you this, but I showed this graph about energy density, mass specific and volumetric specific, and you have the batteries in these graphs always on the low end side, because they have to put all the power inside the batteries. When you look at fuel cells, they get the oxygen from the air. When you look at fuels in conventional powertrains, they also get the oxidizing agents, the air, the oxygen from the air. Batteries need to have all this in this battery itself. So they have to bring the reduction and the oxidization in one package, and this is heavier.
But then to like put it in perspective for the question of like why not just build the electric one, is they're all multiple like parts of the puzzle, and we need all of them.
We really need also this electric infrastructure.
Okay. Very interesting. And maybe back to you, Chiara. There was one question from one of our viewers who wondered, are we sure that this sink agent is really removed from the market if there's nothing that's actually as good?
Yeah, I want to add one thing to the previous answer. Sorry, I don't want to have made it sound a bit like us against them. Like a lot of the time, industry and academia really work together in this field. So there is a lot of cooperation. It's just that generally we focus on different things. So legally it's been removed from the market. You just have anti-wear agents which are not as good, and that is just
isn't there like an incentive to say like we'll try to sneak it in? Would anyone notice if there's this sink agent still around?
Probably, because I think it was creating other problems as well. So I think in the end it was sort of good for everyone to get
so
rid of it.
It's academically fascinating to understand why this was such a good lubricant, but it's not actually the greatest product in the end.
Yeah, so it was a really good anti-wear agent, and we think that the way it works is kind of like decomposed somehow at a certain temperature and form a very stable film, and so I think that's quite understood now. And so the idea is to see, okay, can we get something which is similar, it's like a little branch molecules with like little arms, and these arms detach, and can we get something which doesn't have this I think it was I don't remember what it was, but something which is similar shape but doesn't just create problems and forms the same type of film. And I think we're getting there.
Good, that's an optimistic view on this. There was one question maybe also on the side of like issues that can arise by using a certain product. One of our viewers wondered, are there any associated issues or problems with utilizing hydrogen? Maybe for electric cars we have always a discussion on the lithium for the batteries. Is there anything for hydrogen where it's like, it's a bit of the problem side?
Yes, first of all, fuel cell vehicles also have a very small battery, so it's still this problem, but not that big like in battery electric cars. I think the problem with hydrogen is really that you have conversion process. So you have this high rated electric energy and you convert it to a chemical energy carrier and then convert it back. So if you could, you should always use the electric power through the way until your wheels. But as I said, renewable energy is a little bit complicated with when we have sunny days and no one wants to drive around. Maybe the other way around. But if you don't have this, if you have renewable energy, you always have these peaks and you need to store them. Otherwise, we would lose this energy. And in this case, hydrogen is always a good way. I think one problem maybe in the future is this water, like when we have water shortages and we use the water for electrolysis. This could be a problem. On the other hand, when we have really this water shortage, I think we have really other problems than mobility itself. But there are currently some studies or some approaches to take water from the air, and we are currently working on a methanation step following the hydrogenation step with a plant that can also absorb water from the air and use it then for maybe hydrogen as a electrolysis. So when we think about additional costs, a hydrogen refueling station needs about 100 cars per day to be have the black zero, and about 10 trucks. So you need some cars to have the infrastructure, and you need the infrastructure to get people to buy these cars. But I think really the main problems that could follow with hydrogen are the energy conversion and maybe water.
Interesting, thank you, Karin. There was another question then for you, Kira, from one of the viewers. And the question was whether you could elaborate a bit on what this additive part is to like solve the boundary lubrication issue. How does it push the sides apart? If you could go into that again a bit.
Yeah, so basically you end up having, so these molecules are very polar, and they're really attracted. So the polar hand is really attracted to the surface. So if you just leave your lubricant with this additive in the system for long enough, the surfaces will just be covered with these molecules. And obviously, if you put in high enough density, which you would do, so you would just end up having your surface with this little kind of bristle looking like that, which is sort of, these are the tails. And it actually, if it is dense enough, if you have a high enough density, then just simply by the geometry of the system and the geometry of the molecules, these tails will not interdigitate that much, will just form quite a compact bristle, which really pushes the two surfaces apart. And the shape of this bristle part of the molecules is the same shape as the lubricant. So there's really a good interaction between then the lubricant in the middle and the additive, which forms this kind of like this separating structure. I hope that's maybe
so
clear.
Then just for me to see if I understood it, in a way you don't actually have the things touching each other then anymore, because this lubricant always keeps a minimal amount of distance there.
Yeah, exactly. So that's that's what it is. So you have to have enough of these additives so they can completely cover the surface. So there has to be a high enough density.
Cool. And then to start to round this up, I had one question that I found really interesting, and then I might actually start asking people generally when they come to these talks. Unfortunately, it was an anonymous viewer who asked this, so I don't know who to thank here. But the question was, and I'll ask it to both of you, can you remember what brought you to your field of research? What motivated you to do the kind of work you're doing now?
Should I start? Okay.
If you want to
I always thought about energy and water, the main topics that we have in the future in engineering. These are the main sources that will be, a little bit short in the future. And I did some kind of student work for a fuel cell producer in their laboratory, and it was very fun and very interesting. And so I said, I want to have at least this part also in my studies, and I got this very great opportunity here to start in this field, and I think every day is cool.
Very nice. So go internships there.
Yeah.
Kara, tell us a bit about your story.
So I do computation. I didn't mention this. So I do computer simulations of surface in general. So that's what I've always done, and it's really at the atomistic level. So I model atom by atom. Sometimes really also the quantum mechanical forces which govern the system. So, but on the other hand, I've always been really interested in kind of like the end product. So to try connect these two worlds, which are very far apart, because I can only simulate in a reasonable time really tiny. I mean, you've seen that, I can just do like a tiny speck of the system. And and so I was interested in engineering from one side and this sort of type of simulation on the other side. And I just started collaborating with a professor who is at Imperial, and he was one of the few people at the time, now there's more, about 10 years ago, who was really interested from the engineering point of view in these simulations. And so we started doing some work, and I was hooked. I think it was a really, really cool type of systems, and I kind of like carried on working on that.
Cool. Thanks. And then to round the evening off, is there anything you wish I had asked, or anything you want to let the audience know, anything you want to pitch and promote?
So
if you want to start,
I think
Karin?
in my last slide you already saw we have a lot of projects around the move, and I'm currently not directly working in the hydrogen path. I'm more for the methanation step that we are currently planning. It's called the Move Mega for methane gas. So yeah, and this is my real work with heat management and CO2 absorption from the air, and it's really also interesting to go one step further from power to hydrogen to power to gas. And with this there are a lot of advantages compared to hydrogen, but also disadvantages. So this is also a very interesting topic, and if you think the change stops at hydrogen, please think a little bit wider.
I see it's really worth having professional researchers in this topic, because it seems that it can be complicated sometimes. What about you, Chiara? Anything you'd wish to promote?
So if people were interested in what I talked about, so with my colleague from Imperial, James Ewan, we run a seminar series on tribology, which is called WEST, WESST, and the talks are all on YouTube. Some of them are more technical than others, so I think some of them are really like a real life sort of production of like ball bearing systems, and how they use artificial intelligence to like sort all the machinery, the maintenance, and blah blah, which so there can be like a really different level of technicality. And so if you think you might be interested to check out more about this topic, then yeah, go on YouTube. I think the handle is West Tribo, so WESSTRIBO, and you can check out the videos.
Okay, so given that all of you viewers are on YouTube already, and we're finishing the nanoTalks here, you know where to go next. And with that, it just remains to me to say thank you again. Thank you, Karin, for giving the talk here. Thank you, Chiara, for joining us remotely for this very interesting talk and the Q&A. Don't forget, you can still apply to the Sympact program of REACH at sympact.reach.ch. Applications open until the end of September. And with that, I hope you all have a very nice evening. Goodbye.
Bye.